All right, welcome back to the deep dive. You know we love getting into the weeds of these cutting-edge machine learning papers, and today's pick is no exception.
No, not at all. It really isn't.
We're taking a close look at automatic operator-level parallelism planning for distributed deep learning, a mixed integer programming approach. And that title alone, I think, hints at some pretty heavy stuff.
Oh, absolutely, yeah. We're talking about the nitty-gritty of how to actually make those massive AI models we hear so much about actually work in practice.
Right, because it's one thing to design a model with billions or trillions of parameters. It's a whole other beast to actually train and deploy it efficiently.
Yeah, and that's exactly the problem this paper tackles head on. I mean, think about it. Trying to run those gigantic models on a single machine, well, that's just not feasible.
No, not a chance.
You absolutely need to break down the computation and distribute it across a whole cluster of powerful processors.
So distributed computing is a must, but it's not exactly a walk in the park, is it?
No, it's not a walk in the park at all. This paper makes that very clear. Figuring out how to best split up that work, how to optimize the distribution across all those devices, that's been a largely manual and very specialized process.
So it still requires a ton of human expertise, even with all the advances in distributed computing tools we've seen.
Exactly. And it gets even more complicated with these modern neural network architectures. Things like mixture of experts models and multimodal models. These introduce a whole new level of complexity compared to the simpler networks of the past.
Okay, so before we get too far, can we break down why those newer architectures pose such a challenge for parallelization? I mean, what makes them so different?
Well, think about it this way. Older models often process data in a more sequential manner, like following a straight line. But these newer architectures, like mixture of experts, they have all these conditional paths.
Meaning different parts of the network activate depending on the specific input.
Exactly. So you can't just split the model up neatly into equal chunks and expect everything to run smoothly. And then you've got multimodal models that deal with different types of data all at once.
Like images and text, for example.
Right. So now you have this really complex computational graph with all these interconnected parts and nonlinear dependencies. It's like a tangled web.
Okay, so trying to apply those traditional parallelization methods, just chopping things up into equal pieces, that doesn't really cut it anymore.
No, it becomes much less effective, and you end up with all these inefficiencies, bottlenecks, idle time, you name it.
So even those powerful frameworks we have now, like DeepSpeed and Megatron-LM, they still need a lot of manual tweaking and expert knowledge to make them work well, especially with these more complex models.
Yeah, that's the big issue. Those frameworks are essential tools, providing different types of parallelism. You got data parallelism, model parallelism, pipeline parallelism, but choosing how to combine them, how to configure them just right for a specific model and hardware setup, that often comes down to trial and error by really experienced engineers.
So a lot of intuition and guesswork involved.
Exactly, and that's where this paper comes in. It's proposing a more systematic, automated approach. Can we take some of that guesswork out of the equation? Can we make this process more efficient and reliable?
And their solution comes in the form of a scheduling problem. They're looking at it like optimizing workflow in a busy factory.
Yeah, a really interesting analogy. They're using a technique called mixed integer programming, or MIP.
Now, MIP might sound a bit intimidating to some of our listeners. Can you break down what it is and why it's relevant here?
Sure. So MIP is a powerful optimization technique. It lets you build a mathematical model of a complex problem. And the cool thing is that it uses both continuous variables and discrete variables.
And discrete variables, those are the ones that can only take on certain specific values, right?
Exactly, like whole numbers. And that's perfect for representing decisions that are either yes or no. For example, should this specific computation be assigned to this specific processor or not?
I see. So it's like a binary decision.
Right. And then the programming part of MIP, that's about finding the best possible solution that fits within all the constraints you've defined. Things like the order of computations, hardware limitations, communication times between devices.
So instead of relying on human intuition, they're building this precise mathematical model of the entire distributed deep learning process, and then letting an MIP solver, which is a specialized piece of software, figure out the most efficient way to schedule everything.
That's the idea. It's like creating a blueprint and then letting the computer find the optimal construction plan.
So they've essentially transformed this very complex distributed computing challenge into a solvable mathematical puzzle.
Exactly. They're taking all those questions of how to run the neural network on multiple devices and turning them into equations and inequalities. And this allows them to explore all the different options for parallelization in a very systematic way, potentially finding the absolute best solution.
Now, the paper mentions that they're framing this as a variation of the job shop scheduling problem. That sounds like something out of operations research, not AI. What's the connection there?
Oh, it's a brilliant connection. It's all about finding the right analogy. Think of each individual operation within the neural network, like a matrix multiplication or a convolution. Think of that as a job that needs to be done.
Okay, so each little step in the computation is like a separate task.
Right. And then the different processors in your cluster, those become the machines that can perform those jobs.
Like GPUs and TPUs.
Exactly. And then the way those operations depend on each other, that dictates the order in which the jobs have to be completed. You can't do step 2 before you finish step 1, right?
So it's like a production line.
Exactly. And the goal, just like in a factory, is to minimize the total time it takes to finish all those jobs. In our case, that means minimizing the training or inference time. That's often called the make span.
So the forward pass and backward pass through the neural network, those become like different stages in the manufacturing process.
Right. And you have to manage the flow of data between those stages really carefully to avoid any bottlenecks.
Okay, I'm starting to see how the analogy fits, but solving a scheduling problem of this scale for these huge neural networks using MIP, that sounds like it could quickly become computationally very expensive.
Oh, absolutely. That's a key challenge with MIP. It can become computationally demanding, especially for large problems. But these researchers, they came up with a clever solution. They use what they call a bi-level strategy.
Bi-level meaning 2 stages.
Right. So the first stage is all about simplifying the problem. They use a heuristic approach to merge certain operations together.
So kind of like combining smaller tasks into bigger, more manageable chunks?
Exactly. That way, the MIP solver doesn't have to deal with as many individual pieces. It's a pre-processing step to reduce the complexity.
So it's like streamlining the production line before you even start optimizing the schedule.
That's a great way to put it. And their heuristic is designed to only merge operations that are safe to merge. It won't mess up the overall flow of the computation.
So it won't accidentally create any new bottlenecks.
Exactly. Then, once they've simplified the problem, they apply a powerful commercial MIP solver, Gurobi in this case, to find the optimal schedule for this reduced problem.
So 2 steps. Simplify, then optimize. A smart approach to tackling the scalability issue. Now let's dive into their experimental results. They compared their framework against DeepSeek's dual pipe strategy. Can you tell us a bit about dual pipe and why this comparison was so important?
Yeah, so dual pipe is a cutting-edge pipeline parallelism technique developed by DeepSeek for their large language models. It's known for being really effective at balancing memory usage and computation speed. It uses a clever bidirectional pipeline to achieve that.
Okay, and these researchers wanted to see if their automated system could essentially rediscover this expert-designed strategy.
Exactly. They wanted to see if their MIP framework, given the same constraints as dual pipe, could come up with a similar solution. It's a really important test because it shows whether their system can automatically arrive at sophisticated parallelization strategies that previously required human expertise.
And what were the results? Was their system able to match dual pipe's performance?
It's pretty amazing, actually. Their MIP solver produced parallelization schedules that were very close to dual pipe's strategy, even when they tried it with different numbers of GPUs. They used Gantt charts to visualize the computation on each device over time, and the patterns were strikingly similar. They even had those characteristic bubbles of idle time that you see with dual pipe.
So they essentially replicated a human-designed, state-of-the-art strategy using an automated system. That's really impressive.
But it gets even better. They then decided to see what would happen if they relaxed the performance target a bit. They gave the MIP solver more freedom to explore different solutions. And guess what? It found schedules that reduced those idle time bubbles by half compared to dual pipe, all while staying within the same memory constraints.
So they actually improved upon the expert design strategy.
Exactly. It really shows the power of this approach. Even really well-designed, manually created parallelization plans might not be the absolute best possible solution. There might be hidden optimizations that only a systematic mathematical approach can find.
It's like finding those extra few percentage points of efficiency that can make a big difference at scale.
Right. And they didn't stop there. They also tested their framework on a randomly generated computational graph, just to prove that their approach wasn't limited to specific neural network designs. And again, it performed really well, effectively balancing the workload and minimizing communication time. In fact, when they use two devices, they achieve the theoretical maximum speedup.
So really promising results across the board. It seems like this could be a major step forward in distributed deep learning. To put this in context, we've seen this evolution from basic data parallelism to model parallelism and then pipeline parallelism. Do you think this paper represents the next step in that evolution?
I absolutely do. I think it represents a shift towards greater automation. The models are becoming so complex, it's getting harder and harder for humans to keep up. We need more intelligent tools to help us. It's like in the early days of programming when people had to write in assembly language. Then came higher level languages and compilers that automated a lot of the difficult work.
So this is like the compiler for distributed deep learning?
Yeah, I think that's a great analogy. It takes care of all those low level details like scheduling and resource management so that humans can focus on the bigger picture. We're moving from a handcrafted approach to a more engineered approach.
That makes a lot of sense. Okay, let's recap. What are the key takeaways from this deep dive?
Well, the biggest one is that they've successfully formulated this complex problem of distributed deep learning parallelization as a mixed integer program. That opens up a whole new way of thinking about optimization. The bi-level approach with the heuristic pre-processing and then the MIP solver, that's key to making it practical for real-world models.
So a clever solution to the scalability issue.
Right. And it's a general framework. It's not limited to specific neural network architectures. It can handle all sorts of different models. And it considers all the important factors, not just computation time, but also communication costs and memory limitations. And of course, the results speak for themselves. They were able to match and even improve upon a human expert solution.
So strong empirical evidence to back up their claims. Now let's switch gears and talk about real-world implications. What kind of impact could this have if it gets widely adopted?
Well, I think it could really democratize access to large-scale AI. Right now, only big companies with lots of resources can afford to hire the experts needed to do this kind of optimization. But if we can automate it, then smaller teams and research labs could also train and deploy these massive models.
So it levels the playing field.
Exactly. And it could accelerate innovation. It could free up researchers to focus on the science instead of spending all their time tweaking parameters and trying to figure out the optimal parallelization strategy.
It also seems like it could lead to significant cost savings, especially in cloud computing environments.
Absolutely. If you can train your models more efficiently, you can use fewer resources and lower your cloud bills. And in the long run, it could even pave the way for even larger and more complex AI models.
Because right now, we're limited by our ability to parallelize them effectively.
Exactly. It's a bottleneck. But if we could remove that bottleneck, who knows what's possible?
Okay, now for our favorite part, novel notions. Let's speculate a bit. Based on this paper, what are some interesting research directions that you see emerging?
Well, one that comes to mind is dynamic and adaptive parallelism planning. Right now, they're generating a static plan before training even begins. But what if the computational needs of the model change during training? What if the available resources fluctuate?
So the optimal plan might evolve over time.
Exactly. It would be really cool to develop a system that could adapt on the fly, constantly adjusting the parallelization strategy based on the current conditions.
Like a self-driving car for distributed training.
Yeah, I love that analogy. It would require some really sophisticated monitoring and decision-making algorithms.
And probably some new techniques for migrating computations between devices in real time.
Oh yeah, there would be challenges.
Yeah.
But the potential benefits are huge. It could make training much more efficient, especially for those really large foundation models.
Okay, what's another novel notion?
Another exciting direction is hardware-aware neural network design. Right now, we tend to design the model first and then figure out how to run it on the hardware. But what if we could design the model and the parallelization strategy together?
So consider the hardware constraints from the very beginning.
Exactly. You could potentially design models that are inherently more suitable for distributed training.
It would be like designing a car and the highway system at the same time.
Yeah, that's a great analogy.
Huh.
It could lead to much more efficient AI systems, especially for specialized hardware like TPUs.
So lots of exciting possibilities on the horizon. And just to remind our listeners, these are just speculative ideas. We're just having some fun here.
Yeah, pure speculation. But it's important to think outside the box and imagine what the future could hold.
So to wrap up our deep dive, it's clear that this paper presents a really significant step forward in automating and optimizing distributed deep learning. It has the potential to democratize access, accelerate innovation, and maybe even pave the way for even larger and more powerful AI systems.
Absolutely. It's a fascinating area of research with huge implications for the future of AI.
And we encourage you to check out the paper yourself. We've included a link in the show notes. It's a bit technical, but it's worth the effort if you really want to understand the details. And as we move towards more and more automation and AI, it makes you wonder, what's the future of collaboration between humans and machines? How can we work together to shape these increasingly complex and powerful technologies?
A big question to ponder. And on that note, thanks for joining us on the Deep Dive. It's been a pleasure.
Always a pleasure. Until next time.